Okay, well, thank you. You are the hardcore OSCAL fans at this hour. So thanks for being here. There you go. We're going to spend a little time, hopefully tying a lot of the concepts you've heard together today. We're going to talk about Kubernetes, which is a very complex system. We'll get into that shortly. A few seconds more about my perspective on this problem. As the Cloud Native Computing Foundation is the custodian of the Kubernetes project, we are responsible for maintaining the open source repo and responding to security alerts, et cetera. And then in my role at SunStone, we help CSPs as well as agencies understand how to have Kubernetes compliance and how to structure that in their mission. I'll hand that over to my co-presenter.
Thank you very much. I'm Francesco. I'm a security engineering manager at ControlPlane. My life, I did a lot of studying, and then I moved to the UK, working for the European government first, and then for a large satellite mobile provider. And then more recently, I joined ControlPlane. We are a cloud-native security consultancy established in London in 2017. We are security specialists in, guess what, Kubernetes, but container security in general, and we are focused on deeply threat-modeled, secure by design and secure by default cloud-native architectures, such as Kubernetes.
Great. So we realize that every minute we talk, the blood sugar is going down, the caffeine is going down, and we're standing between you and cocktails, so we'll try to keep it as short as possible. So we'll go through a little bit about Kubernetes for those who don't know it, and then we'll talk a bit about how we threat model Kubernetes and why that's important for OSCAL. And then we have a little demo at the end. So what is Kubernetes? It's been called the cloud, the operating system for the cloud. It's an orchestration engine for containerized workloads. Some think of it as a multi-cloud solution if you want to lift and shift from on-prem into the cloud and in multiple clouds. So it fills a lot of use cases. A lot of growth over the past several years. It has a lot of promises on the value proposition. I would say really the paradigm-changing thing is recognizing that at its core, everything is code. So once you build up the data center or the hypervisor environment to run Kubernetes, the operation and the deployment to it is all in code. And we can get into some examples later, but that's really a game changer for how you think about compliance and operations and all of the topics we've discussed today. What this looks like, it's an API at its core, and it's an API that creates data in a key value store, and that's your system at the heart. Everything in that key value store represents something that is going to be provisioned or has been provisioned to run a workload. On top of that is a constellation of other services that respond to different parts of that API that proxy various components and act as the practical gears and mechanisms to run those workloads across the server nodes, across infrastructure, even across clouds. Now, a Kubernetes IT person might see this very differently. They're used to standing up either those servers or a hypervisor environment and setting up all the VMs. And they've probably been looking at the applications that they need to run, and then they have to procure and provision storage and networking and infrastructure. Developers, they see Kubernetes in a very specific way. It's an easy button to deploy applications at scale and not have to worry about all that operations and maybe not even worry about the security part. The big question for this audience is probably how attackers see Kubernetes. To them, what's the new weakest link? It's the developer. So now I can do my reconnaissance on an organization. Maybe I'm using fancy ChatGPT to craft phishing messages. I just have to get that credential that gives me into the Kubernetes API. And then I have all sorts of fun. And then for some of you in the audience, this might be your perspective. So what is this thing that my developers have brought me? And how do I go about securing it, reasoning about it, and making sure it's compliant? So I think our next part, we wanted to talk about how you can use the threat model for Kubernetes to really ground the OSCAL development and operationalization. So when I talk about a threat model, I'm not talking about vulnerabilities. I'm not talking necessarily about a specific attack chain, although those frameworks are very useful. I'm really talking about what is the complexity of the system. What are the data flows within the system? What are the actors who have to operate it, who have to provision it, who have to secure it? And are you addressing all of those promised benefits judiciously with what are the risks to those system components failing? What are the risks of compromise to those system components? And of course, attackers, as I mentioned, they're paying attention to all of this as well. So they're availing themselves of all the automation that we've been discussing today. They're using it on the attack side. So you have to have a perspective of how you level up your game. I'm going to have Francesco talk a little bit about the methodology behind threat modeling.
Thank you very much indeed. So as part of a threat model exercise, we fundamentally ask ourselves, what can go wrong in the system we are trying to build? And to answer that question, we identify basically 4 things to derive from the exercise tactical and tangible data that we can then action upon. So we had tried to identify scenarios, starting points for the threat modeling exercise. They should consider sensitive data flows and communication flows. And then we try to identify what are the applicable threats to our platform, to the platform we are building. And so you define your top threat statements, but the recommendation is always to map back to the business risk. So you can articulate that risk at different levels within the organization. And then we try to derive attack paths. And those are literally the steps that bad guys out there, they have to perform to get to your crown jewels. And based on the attack paths we identify, we then actually derive attack trees, and we generate visual representation of threat models. Word of caution, attack trees can get real complex real fast. This is an attack tree we open source, was done for a customer, and that shows how many steps an attacker can do. And the idea is that at the end of the threat model exercise, you fundamentally derive security controls. To do what? To break the attack chains. So to make the attacks not possible or not easy to actually perform. So at the end of the threat model, what do we want? We want controls. And where we find controls, in something great as NIST 853, for example. This is a real-world example. The threat identified on this specific deployment was a hostile tenant attacking another tenant, aka a compromised pod pivots over the network to move laterally. Again, Kubernetes is a multi-tenant platform. Not all the tenants are trusted equally. So what are the applicable controls from the NIST 853 standard to mitigate that threat? Well, many. 2 we are selecting today for the sake of this presentation. AC6 leaves privilege for the workloads running on your cluster, and SC8 transmission confidentiality and integrity over the wire between workloads. Their implementation in Kubernetes is translated into not allowing privileged pods, privileged workloads, and implementing a default deny network policy across your namespaces. How do we want to do it? Of course, we want to do it via OSCAL. Another word of caution, Kubernetes, complex platform, as Rob said. The capabilities are many. They're stacked into different layers. It is really important that you scope down the hardening of your cluster to those features that are required to mitigate threats. So again, it's a portfolio of things that are available to you. Just pinpoint the one you want to tackle based on the threats you identified as part of the threat model exercise. Right, so OSCAL. OSCAL fits nicely, real nicely, into a larger ecosystem of everything defined as code. So you got policy as code, you got your compliance and controls as code, OSCAL, and then the risk assessment rules as code, automating compliance checks on infrastructure and policies, and then eventually you have infrastructure as code, pipeline as code. So everything, the idea is to achieve something which is very deterministic. So if you store your files into version-controlled repositories and you use tools to basically implement that into the real-world deployment, you achieve a high degree of determinism you can do it in an automated fashion, and more importantly, you remove the humans from the equation. You don't need people to connect to systems and deploy things. They just have to connect to the relevant repositories with the right access control in place. So how would you implement efficiently, in a secure by design and a secure by default fashion on a Kubernetes cluster those controls? Well, we use policy enforcement engines for Kubernetes or compliance engines. One example is Kyverno. And the way it works, you have Kyverno policies stored somewhere, again, version control repository. Those policies are applied by the Kubernetes API, the brain of the cluster, as Rob mentioned. Those policies are then sent to the Kyverno engine, which enforce those policies and securing your cluster, again, by default and by design.
Yeah, and I just wanted to double click on this notion, as I said, that everything is code, that allows you really to shift left, as the industry now calls it. You're enforcing these controls in code, right? So you have, for example, a network policy requirement. When your developer is handing that off to the operations team or the DevOps team, they can write, in this case, Rego, which is for another policy engine called Open Policy Agent. You might have heard of it as Open Policy Agent Gatekeeper or OPA Gatekeeper. So they can write corresponding rules to check the requirements for that networking. And at either pipeline time or even further along when you're in the Kubernetes API space, at a time we call admission control, that policy enforcement point can reject that admission before it ever gets deployed into the cluster. So again, you're moving from a paradigm that is trust but verify to deploy in a secure mode by default. And then verification really becomes more around, are you putting the right code in place? Are you reviewing that code before it gets deployed? So just as another example to drill down on, this is an actual Azure Kubernetes example where they have a policy requirement to enable RBAC, the role-based feature in Kubernetes as a certain requirement for a certain flag. So a little bit of a messy slide, but what you can do is you can trace from a human understandable document to a specific deployment artifacts, in this case a Terraform plan, that's part of your CI/CD pipeline. You can create that policy enforcement rule set that checks, is this an Azure Kubernetes cluster? Great, then it has to have that role-based access control equals true, and then of course we can tie it all back to OSCAL. So with that, and we wanted to talk a little bit more about OSCAL.
Thank you very much. So real quick, back to the threat model. As part of the exercise, we derive controls, right? And as I said, we want to apply those controls in a structured way and in a programmatic way. So we come from NIST, we derive an applicable profile to our cluster, and then for the individual component of the cluster, we draft the component definition files. Again, an example of a component definition for the spot specification, implementing AC6 NIST control. The document looks like that. So we have a reference to the control IDs from the profile. We then have a reference to the specific OSCAL profile, the applicable one. And then here is how we implemented it. And for the sake of this presentation, we chose to implement it using a Kyverno policy, again, that compliance engine. And this is, again, how AC6 can be actually implemented on the cluster itself to make sure that least privileges apply to workloads and they cannot run as privileged ones. Again, end-to-end, how does it look like? OSCAL repository, Anka mentioned a way of organizing documents, which was very, very effective. Catalog profile component, and then on a separate repository, this is the way we usually do. We derive Kyverno policies stored in another repository, apply those policies, they get loaded on the compliance engine. The engine then enforces them across your cluster, and then you have an external compliance tool can actually do the validation of the implementation of those controls with a number of ways. And the same, again, going back to the two controls we selected from the threat model, AC6 and SC8. This is, again, a component definition file for implementing SC8 using a Kyverno policy, enforcing every namespace across the cluster to have a default deny network policy, so avoid workload to workload unauthorized network communication. Back to you, Rob.
Yeah, I just wanted to present a bit of an overview tying back to our discussion on the threat model. So why I see the threat model as being the glue to making all of this work is that you can tie your components and your system inventory and your controls all together. So just to summarize how we've done this with the Kubernetes project, we have OSCAL component defs maintained in a repo. And actually, I'll add a little bit more context there. In fact, we initially started crafting manually the YAML or JSON OSCAL for each of those components. But then we realized, well, Kubernetes is kind of ahead of the curve of producing releases with an SBOM, SPDX output. So we decided, well, we can use that SPDX SBOM file as an input. And in this case, we used that open policy agent, Rego, to construct the component defs on the fly. So every time a Kubernetes release comes out, it releases an SBOM. That Rego policy rule, which we're putting on the open source repo, will generate those component defs. So you can keep the component defs themselves in your repo, or you can keep the code that generates the component defs in your repo. I'd like to point out another nuance that we use in terms of how we organize the components. That's been a discussion, long-running discussion today. So we think of components both in terms of the functional components in the Kubernetes ecosystem, the API server, the kubelet, et cetera. But we also think in terms of the security capabilities that you need in the system to protect. What provides the encryption, what provides the secrets management, what provides the network controls. So we add those to the component defs as well. And then again, in a running Kubernetes system that's stood up, we have that runtime API providing the telemetry and the inventory of what components are up, what pods and workloads are running, and then we can map that to the component definitions and the security capabilities to make sure that those are all meshed. But to contextualize that and make that understandable both in terms of literally mapping things in the code, but also to the human user, that's where it comes back to the threat model. So if we can tag at each of those steps, functional components are threatened by certain TTPs. Security capabilities defend against certain TTPs. My inventory has been scanned, has been enriched with certain TTPs. I can now bring all that together in my model and tag the OSCAL. In fact, I'll show in the next. You can add those threat IDs explicitly to the OSCAL. Here we have it in the back matter. We're kind of moving maybe more to a props-based encoding. But now you've got traceability throughout all of those artifacts and through the whole process with that threat model and a particular framework, maybe a MITRE attack or something as that glue. And then I think to really maybe wrap up the whole conversation for the day, the main event, this is kind of how we're approaching an end-to-end continuous compliance regime for Kubernetes. So starting at kind of the 11 o'clock, we talked about you're going to have your component definitions either handcrafted, machine-generated, or code-generated. You're going to maintain those in your repo. Moving counterclockwise, you're going to then generate those policy enforcement rules, whether it's the Rego for OPA, or Kyverno's rule set, or CEL from Google, and you're going to use maybe some advanced technology. We've used things like Neo4j, as have others with OSCAL, to kind of model the relationships between the components and the threats. We have done some experiments with large language model, not ChatGPT, but similar technology. And I mentioned the MITRE attack as a framework that we've used explicitly. And as we've shown, you're embedding in the OSCAL those links to the policy enforcement rules. So that way, when a Kubernetes system is deployed, you've already armed it with all the enforcement decision-making it needs to prevent out-of-compliance components from being deployed, or even entire Kubernetes clusters, as we showed with the Azure example. Yeah, and then at the end, you're collecting all this rich data from Kyverno, from OPA, from all the security tools, maybe third-party vendors, and you're able to tie it back to your security assessment results. I probably skipped the plan part, but you generate the plan, you collect all the evidence, and then you generate your result. And so we hope to see this mature in the Kubernetes release lifecycle so that all of these artifacts that are not system runtime specific are part of the release. And then you, as a Kubernetes operator, when you install it in your hypervisor or your data center, you can add the runtime components and then generate your full SAR from that. I think we're on to demos.
It's showtime. So how are we doing with time? Pretty well. As I said, we have two demos for today. They go back to the two controls we intend to implement from the NIST catalog. So the first one is, I need to sort of operate this video manually, right? So the first one shows a manifest for a privileged pod on a cluster which was not secured using, again, the Kyverno policy. And if I can find the cursor. So as I try to deploy my workload on a cluster which wasn't hardened, it goes ahead, and of course the workload is provisioned and is running, which is undesirable. Where we go next, so we delete the pod, and instead we apply, from the OSCAL definition, we apply that policy which would prevent cluster-wide any privileged workload from running. So we only want to allow non-privileged pods, implementing correctly AC6, the control. So now the policy is applied, and as I try to deploy the pod itself, I receive an error message, of course. And of course, a regular pod instead, non-privileged, can instead, is unaffected, can run smoothly, so the policy doesn't prevent that from running, of course. So assuming AC6 is correctly implemented, let's see how we can then do the same for SC8. Again, this is a, it's not loading. Is the same. There we go, next one. So what we have here, we create a namespace on our cluster called unsecure namespace. And of course, because the cluster is not hardened yet, by default, the namespace itself doesn't have any network policy associated, which again, it would be a violation, it would be a non-compliance against SC8. So what we do instead, again, using OSCAL, using the component definition file, if I can find the cursor, we apply the Kyverno policy, which would require a default deny network policy applied by the administrators across each namespace. But we do more. What we do, we also generate a new, we create a new policy to make sure that Kyverno actually enforce a default deny policy for every new namespace being generated, hence implementing secure by default. So, and we can see that as an administrator creates a new namespace now, called secure by default namespace, the namespace indeed has a default deny network policy attached, even if they forgot to do it. Hence realizing the secure by default design. Trying to deploy a pod in the unsecure namespace is a violation, not allowed. Trying to deploy the same pod in the secure by default namespace with the default deny network policy attached goes through, and the workload is now up and running. We got still time for a few questions because this is almost the end of the presentation.
Yeah, just to summarize, Kubernetes is very complex, but it's very powerful. Use that declarative power to your advantage. Use these OSCAL models mapped to your threats so that you drive policy and a virtuous loop between the policy, OSCAL, and then assessment. And so we'll take questions.